This talk is about an algebra of logic. But what does that mean? What does it look like? And how does it relate to our usual algebra? What is set theory? And how does that fit into our story? And what is Boolean algebra? And why is it of interest today? Let's start by looking at the laws we take for granted when calculating with numbers. We all know that 4 plus 3 equals 3 plus 4, and in general that any two numbers can be added in either order. For any numbers x and y, x plus y equals y plus x. And the same happens for multiplication. X times y always equals y times x. These are the commutative laws for arithmetic. But subtraction is not commutative. 4 minus 3 is different from 3 minus 4. If we now have three numbers, we can add the first two and then the third. 4 plus 3 and then plus 2 gives 9. And we also get 9 if we add 4 to the sum of 3 plus 2. And in general, x plus y plus z equals x plus y plus z. And the same happens for multiplication. These are the associative laws for addition and multiplication. We can also combine adding and multiplying in the distributive law. 4 times 3 plus 2 equals 4 times 3 plus 4 times 2. But we cannot switch plus and times. 4 plus 3 times 2 is not the same as 4 plus 3 times 4 plus 2. And finally, the numbers 0 and 1 play a special role in arithmetic. For addition, if we add 0 to any number in either order, we don't change it. And if we multiply any number by 1, we don't change it. Also, any number times 0 is 0. In 1854, the mathematician George Boole published a book called The Laws of Thought on the mathematical foundations of logic. In this groundbreaking work, he aimed to replace our traditional algebra by an abstract system where other things replaced numbers. This was his algebra of classes. Suppose we have two classes of objects, which might be anything, numbers, people, or anything you choose. If these are x and y, Boole defined their product, x times y, to be the class of all things belonging to both x and y. As an example, he took x to be the class of all white things, and y to be the class of all sheep. Then x times y is the class of all white things that are sheep, that is, all white sheep. Well, y times x is the class of all sheep that are white things, which is also all white sheep. And in general, we have the commutative law, x times y equals y times x. What about an associative law for classes? If x and y are as before, and if, as Boole suggested, z is the class of all horned things, then x times y times z is the class of all white sheep that are horned, while x times y times z is the class of all white things that are horned sheep. And these are both the class of all white horned sheep. There are other links with the algebra of numbers. We've seen that any number times 1 is itself, and any number times 0 is 0. Here we let 1 be the class containing everything. Boole called this the universe. And 0 be the class containing no things, which we may call the empty class, such as the class of all pink elephants. Then x times 1 is the class of all things in x which are also in the universe, which contains everything. So x times 1 equals x. And x times 0 is the class of all things in x which are also in the empty class, which contains nothing. So x times 0 equals 0. But unlike the algebra of numbers, we have a new law, the idempotent law. X times x equals x, or if you prefer, x squared equals x. Here, the class of all things that are in both x and x is just the class of all things in x. So x times x is always x. But this doesn't happen for our number system, where if x squared equals x, then x is either 0 or 1. Boole also defined the complement 1 minus x of any class x to be the class of all things that are not in x. It follows that x times 1 minus x is the class of all things that are both in x and not in x, which is just the empty class 0. So we've seen how to multiply classes. Can we also add them? Boole said that if x and y are classes, then their sum, x plus y, should be the class of all things that are in either x or y, but not in both. This is the exclusive use of the word or, which we use when we're asking, would you like a cup of tea or coffee, expecting an answer of one or the other, but not both. For example, if x is the class containing the numbers 1, 2 and 3, and y contains 3 and 4, then x plus y contains 1, 2 and 4, but not 3. Boole then showed that his sum of classes satisfies both the commutative and the associative laws. But what about the distributive law, which combines the product and the sum? Here he found that there are two distributive laws as shown here. The first corresponds to the distributive law for numbers, but as we saw earlier, the second one fails when calculating with numbers. Boole's motivation for his algebra of classes was to apply it to logic, and we can give an example involving syllogisms. A syllogism consists of two statements which lead to a conclusion. For example, the Greek philosopher Aristotle combined the two statements, all men are mortal, and Socrates is a man, to conclude that Socrates is mortal. Wishing to apply his algebra of classes to syllogisms, Boole combined the statements, all x's are y's, and all y's are z's, to conclude that all x's are z's. To do so, he noted that the statement, all x's are y's, means that everything in x is also in y. And so x times y, all the things in both, is just x. And in the same way, the statement, all y's are z's, means that y times z equals y. So now let's look at x times z. Because x equals x times y, this equals x times y times z. And by the first distributive law, this is x times y times z, which is x times y, and that's just x as before. So x times z equals x, which tells us that all x's are z's, as Boole wanted. How does all this fit in with set theory? If you've met set theory before, you'll find Boole's algebra of classes to be similar, but with a difference. In 1874, the German logician Georg Cantor introduced a set as any collection of objects, which he called elements. Then, given any two sets x and y, he defined their intersection, written as an upside-down U, to be the set of all elements that are in both x and y, and their union, written as a U, to be the set of all the elements that are in x or in y or in both. This union differs from Boole's x plus y because instead of his exclusive or, x or y but not both, as in would you like tea or coffee, we now have the inclusive or, x or y or both, as would you like milk or sugar in your coffee, expecting an answer of one or the other or both. We can then check the commutative and associative laws as before, and again we have two distributive laws. We also have two idempotent laws. The set of all elements in both x and x is exactly x. And the set of all elements in x or x is again x. We also have identity elements and complements. Let U, the universe, be the set of all elements we're considering. And let the symbol shown here be the empty set containing no elements. then the set of all elements in both X and the universe is just X. And the set of all elements in X or the universe is the whole of U, with similar rules for the empty set. We can also define complements. The complement of a set, often written X dash, is the set of all elements in the universe that are not in X. So the intersection of X and X dash is the set of all elements that are both in X and not in X, and so is the empty set. And the union of X and X dash is the set of all elements that are either in X or not in X, which is the whole universe. And there are other laws, such as the complement of X dash is X itself. The complement of the universe is the empty set. And the complement of the empty set is the universe. We can also prove two laws named after the Victorian mathematician Augustus de Morgan. For any two sets X and Y, the complement of their union is the intersection of their complements. And the complement of their intersection is the union of their complements. This is all getting rather wordy, but we can use pictures to illustrate what's going on. These are called Venn diagrams, after the logician John Venn, who introduced them in 1881. If X and Y are sets, then their intersection is the shaded region at the top left, the overlap between X and Y. And their union is the shaded region to its right. We can then illustrate other results. Below on the left, depicting one of De Morgan's laws, the surrounding box represents the universe. The shaded region is the complement of X union Y. And you can check that it's the overlap between the part that's not in X and the part that's not in Y. And on the right is one of the distributive laws, where the shaded region is the union of Z with the intersection of X and Y. And you can check that it's the overlap between the regions Z union X and Z union Y. So we've seen Boole's logic of classes and Cantor's theory of sets, and we can generalize these simultaneously through a general concept known as a Boolean algebra. Don't worry about all these details. It just consists of a set together with three operations: cup, which corresponds to the union of sets; cap, which corresponds to intersections of sets or Boole's multiplication; and a dash representing the taking of complements. These operations must then satisfy all these laws which correspond to those we had before. And using them, we can prove results that resemble those we saw earlier. Boolean algebra came into its own in the 1940s, when it was found to be the natural mathematical setting for the design of switching circuits, which in turn led to the digital age of the computer. For example, if we have two on-off switches X and Y and place them in series, as shown below on the left, we can represent this by X cap Y, because for current to flow, both X and Y must be on. This is called conjunction, or X and Y. Or if we place X and Y in parallel, as shown on the right, we can represent this by X cup Y, called disjunction, X or Y, because either switch can be on. And if a switch X is on, its complement X dash must then be off. This is negation, or not X. We can then represent various switching rules by formulas. For example, two X switches in series have the same effect as a single X switch, corresponding to X squared equals X. And the commutative law X cup Y equals Y cup X said that two switches X and Y in parallel have the same effect when we interchange them. This link between the Boolean rules and switching circuits was recognized in the 1940s by the American mathematician and electrical engineer Claude Shannon, shown here. And we'll end with two examples to show how switching circuits can be simplified by using Boolean algebra. In our first example, switch X is in series with the two switches Y and X' in parallel. So the whole circuit can be represented by X cap Y cup X' as written above. But using our Boolean rules, we can show that this equals X cap Y. And so the circuit can be replaced by the simpler one of X and Y in series. So current can flow in this circuit only when both switches X and Y are on. And in a similar way, the circuit below can be written as on the left of the equation appearing above it. Using our Boolean rules, we can then simplify this to X cap Y cap Z', giving X, Y and Z' in series, so that current flows only when the switches X and Y are on and the switch Z is off. We've come a long way since George Boole wrote his laws of form. One wonders what he would think if he were to witness the modern electronic world to which his deliberations naturally led. Thank you for listening.